So, the chemist perspective though, this is where you want to end up when you're thinking about an atom. We have a nucleus, we have this very small, very dense portion, which is where our protons and neutrons are. Remember, those are by far the majority of the mass of the atom. And then we have electrons flying around outside of that. And so a little bit more perspective on what this would actually correspond to if we try to think of it maybe in terms of lengths and distances that mean something to us. So if we took a baseball stadium and tried to think about, our electrons flying around in this whole stadium, how big do you think the nucleus would actually be in this? Any guesses?
Something really small. It's tiny.
I can't hear you.
Really, really small.
Yes. So it's not quite microscopic. It is something we can think of, but it would be like a marble sitting in the middle of this thing. So you'd have a very small something, a very small object, something we can kind of conceptualize of, but you'd have electrons flying around, hundreds of yards away, and then, just that centimeter-sized sphere in the middle, which would be what contributes the force to all of these motions. And then one more, just to confront, again, this solar system idea straight on. How do you think an atom compares to, the kind of scale of an atom compares to the scale of our solar systems? So a little bit of this is arbitrary. So I took the solar system radius to be the distance up to Neptune. And there's obviously these are elliptical orbits, so there's a little bit of trickiness involved in that as well. But if you can suspend your disbelief, if I take the ratio of the radius, so the radius of the entire atom, to the radius of just the nucleus, I get this value here, this value here. And I can do the same thing for the solar system. So the entire solar system all the way up to Neptune, and then the radius of the sun, I get this ratio. And you can see they're actually pretty similar. So I think you guys were calculating percent differences yesterday or the day before. These are only about 30% different. So they're relatively similar. So in some ways it is perhaps useful to think of, this very dense center, the sun that has all of this mass to it, and that contributes the force to keep these things that are many, many times its radius flowing around it outside. But again, the forces that contribute to these things are very different. And so to think of, these discrete planets and objects flying around the sun in the same way that we think about atoms is not the most useful thing. But in terms of size, scale, they are actually very similar. Does this make sense to you guys? Okay. So I think hopefully we have an understanding of what an atom actually is. So atoms are this nucleus that have protons and neutrons in it, and then we have electrons in this cloud around them. Now, what is it that actually distinguishes hydrogen from helium, lithium, and so on? What is the innate kind of property or characteristic of these different elements that separates them from each other?
The atomic mass.
Yeah.
Number of electrons, neutrons, protons.
So there's one of those in particular that's important, and the other things are kind of
Electrons?
variables. No. There's two more guesses, right?
Yes.
And I heard it back there somewhere, protons, yeah. So, as we're going to see as we move along, you can change the number of electrons, you can change the number of neutrons, and you'll end up with the same atom, but it'll have different properties, different characteristics. But the thing that defines, say, hydrogen is that it has one proton. The thing that defines helium is that it has two protons, and so on. So if we look at the periodic table, these things are organized or labeled in such a way that each one has a set number of protons. And that's what these names are telling you. And so that's what I'm saying down here. And this value, the number of protons, is sometimes called the Z number. I don't really understand why people want to call it the Z number. I always forget it and it ends up confusing me. But if you see Z number, it means number of protons. Okay, so yet again, here's the periodic table. And you can see hydrogen up here, helium, and you can see they're labeled with 1, 2, and lithium is 3, beryllium is 4, and so on. And so that number is telling you the number of protons that are in those different elements. Okay?
And that's referred to as the atomic number?
Yes.
It is, okay.
All right. So the Z number is what distinguishes these things from each other. But how do the neutrons and electrons come into this? We know they're important parts of the atoms, they're definitely there, so presumably they play some role in what's going on. But what role do the neutrons and electrons actually play? The properties of the atoms obviously depend sensitively on protons. That's what defines one atom versus another atom. But what role do the neutrons play? Do you guys have any ideas? And this is actually a more difficult one to answer. So we can have atoms that have different numbers of neutrons in them. We call these different things isotopes. And so in terms of hydrogen, there's 3 naturally occurring isotopes. So there's the hydrogen that, for the most part, everything we encounter contains hydrogen 1,1, or just normal hydrogen. So there's 1 proton and no neutrons. So the bottom number here is telling you how many protons are in this atom. The top number is telling you the number of protons plus the number of neutrons. So this would be like 1 proton plus 0 neutrons. And then the next most common one is deuterium, which is not that common, but about 0.015% of all hydrogens are deuteriums. And this one is stable and it occurs, and it's obviously slightly, well, twice as heavy as hydrogen. And then tritium also occurs. It's radioactive though, so I have a dash for its natural abundance, because whenever tritium is formed, it will decay with some half-life to form hydrogen. And so it actually doesn't persist, it'll end up decaying to the other ones. And so maybe this will hint at you why the number of neutrons is important. Anyone have any guesses now?
Again, the top number is?
The top number is the number of protons plus the number of neutrons. So for hydrogen 1, there's 1 proton and no neutrons, so there's a 1 on top. And then for deuterium, there's 1 proton, 1 neutron, so there's a 2, and so on. And so from this progression, I think you can see, particularly these 2 are stable, this one is unstable. As we change the number of neutrons, it affects the stability of this atom, and it ends up resulting in a radioactive atom. And so the number of neutrons, it's a sensitive, it's a kind of esoteric, I guess is the word I'm looking for, has an esoteric effect on the properties. But what ends up happening is there's this kind of stability range where as you increase the number of protons, you need a different number of neutrons for some reason in order to make a stable element. And so we're going to look at that a little bit more in the next few slides. But you can vary the number of neutrons in these things. And actually, so these ones occur naturally, but in labs people have made isotopes going from 4 all the way up to 7. And these things have very short half-life, so they'll decay very quickly. But nonetheless, you can make these things. They just end up falling apart because it's not stable to shove that many neutrons into a hydrogen atom. And so, I think I might have already talked about all of this. So again, we have these isotopes. The bottom number, which actually oftentimes if you look at elements, this bottom number will just be left out. Because if I have H here, that means this bottom number has to be a 1. So we have a hydrogen here. It has 1 proton in it, which it has to have. And the top number is the number of protons plus the number of neutrons. And these different isotopes end up giving rise to different kinds of stability. We're going to talk about that in a minute.
Question, so when it falls apart, that means that the parts that were there went somewhere else to bond with some other
It's going to
element.
break apart and it's going to eject a neutron or it's going to eject other things, yeah.
But the neutron goes to be with somebody else though.
It could, yes. So this is the essence of like a nuclear reactor, right? We're going to set these things up and we're going to force them to shoot out parts of their cores or electrons or sometimes it's electromagnetic radiation. Something's going to happen and they'll break down and then it can react with other things. This is sophisticated stuff though.
So to answer the question, why are there neutrons? It's to create stability, or they just occur as a stabilizing force or entity?
Yeah.
Okay.
And I think following kind of the empirical evidence will help with this. So the next slide, I think, yes, is a table of periodic table of the isotopes, I think it's called, or a table of isotopes. And so this is a plot of the Z number from before, so the number of protons that are in an atom versus the number of, or the isotopes for that atom. So this is number of neutrons. So down here at the bottom, we would have, at 1, we would have hydrogen, and hydrogen has those 3 isotopes that we talked about before. Yeah, and only one of those is stable. So there would be one black dot down there which corresponds to stable. And then you can see as we follow this line up, looking at each different atom or element, we can look at this, the number of neutrons that can form that can be in the nucleus of those. So we can look at the various isotopes spread out along this, and the black ones at every point, or the black ones along this plot, correspond to the stable isotope. Okay, and so you can see as you move up it, it's not a perfectly 1-to-1 ratio. As you get larger and larger atoms, you end up needing more neutrons in order to keep the atom stable. And so you can see this has a slope of a little bit over 1. I'm not sure what the slope is, but maybe about 1.5, a little more than 1.5. And you can see as you add in more protons, you need more neutrons to keep those elements stable. So the neutron, it doesn't interact via the electromagnetic force, which is the important interaction between the protons and electrons. But it sits in this nucleus, provides mass, obviously, it's very massive, and it somehow imparts stability on the atom.
So the blue, to interpret the graph, I'm looking at the color scale on this
Yeah.
side, and that looks like a whole other set of questions. But
It is.
yeah.
But it's not hard. We can
Okay.
answer it.
The blue represents isotopes
Yes.
for any given atomic number. Okay, so the green are slightly unstable, the further you stretch out, the more unstable it is.
Yes, exactly. So down here are the most unstable things, and so what we're looking at are all the possible isotopes here at about Z number 60. So this would be whatever element has 60 protons in it, and then you can form all of these isotopes along here. So there's from 60 or maybe 65 neutrons in this, all the way up to 95-ish. But the only ones that are stable are right around 80. And so the ones that are stable will persist indefinitely. They won't break down via some sort of radioactive decay. But these ones at the edge, so they're blue, and like you said before, we can look at this scale bar on the side, and you can see that they only persist for about 10 to the minus 2 seconds.
Okay,
So
so
about
that
0.01 seconds, and these things will disappear.
Which answers my other question, which is what is the scale describing? And that's
How long they'll persist. Yes.
Cool.
It relates to how long. Any other questions? So this is really all I wanted to say about neutrons. They're there, and they don't play a big role. They don't play any role in the electromagnetic force, but they obviously do play an important role in how atoms are stable. Okay. All right. So we've talked about protons. Protons are what define these different elements for us. We've talked about neutrons. We understand that they impart some sort of stability to these different elements. What role do the electrons play? So does anyone have any idea why we organize the periodic table this way? Why isn't it just one big long line, or why isn't it a nice square? Why isn't it a rectangle that would fit?
They're in
a
family.
shape? What was that?
They're in family.
And what does family mean? What does that correspond to?
The kind of there's like metal, non-gas, gases.
Yeah. So you're describing properties that would arise from something. What do you think causes them to behave similarly? So they, yeah, there are families that behave
How
similarly.
they're found naturally, how they're found. No.
Not really.
They're grouped in families according to physical properties, but the physical properties are, let's see if I'm guessing, have to do with the number of electrons to protons and
Maybe let me redirect it a little bit. So we are definitely talking about electrons here, right?
It's been a few decades, so.
Oh, no.
What they can bond with.
So everything you guys are saying is correct, but I think it's the step after what we're talking about, what we want to talk about here. So we're interested in what role do electrons play in the atom. And so electrons are going to be in these atoms in some way. Yeah, they definitely impart the negative charge. So they're going to exist in these atoms in some certain way, and the way they exist is going to be what gives rise to this.
They're numbered, these elements too, so important. But they also.
What do you mean by rings?
Each electron has
yeah.
how it goes, the shell
Exactly.
has
So
numbers.
there's those different clouds. Those clouds are what chemists call orbitals.
Okay.
And these different orbitals, cloud is fine. We can call it cloud if you want. And there's different orbitals are what give rise to this structure of the periodic table. So for these small atoms, hydrogen and helium, they have one orbital in what we're going to call a valence orbital. So one outermost orbital. We're going to define these terms a little bit more over the next few slides. But then on the next row, we have more orbitals available in this valence shell. And so we're going to have more atoms there. And it's going to be similar, the same number for the next one, and then the transition metals will pop in, which means there's even more orbitals available. So the reason we put the periodic table together this way is because of the way the electrons end up filling in around the atom, and this corresponds to the kinds of clouds that are there, or the orbitals. Okay? So, hopefully you have an idea of what's coming next. Now we're going to try and be a little bit more precise.
Who was it who first came up with the periodic table?
I think it's Mendeleev?
Yeah, he was not aware of these orbitals at all.
No, so he
worked
did
with-
what you guys are actually doing. He looked at the properties of atoms, and he was able to back out that there must be something similar about all of these atoms in, say, this row. And when he actually put it together, he put it together on its side. So he would be, I think, looking down this way. So if you look at Mendeleev's periodic table, it looks different than this, but he's just constructed it on its side. And all he's done is looked at these different things. So say if you start at carbon, carbon behaves very similarly to silicon, which behaves similarly to germanium. And he took these relationships and he was able to construct them in such a way as to put together these families that correspond to these, something that's similar about these things. And then coming back along later, we were able to realize what's similar about them is the way that the electrons fill in, the orbitals that are there. You guys follow so far?
Yeah. So that symbol that really is not true, at least gives us an idea about
Which symbol?
the symbol, the one, or,
Oh, the.
yes.
When you see the orbitals, I think you'll think that less. But
I know,
yes.
but at least it gives you,
It gives you a sense of
Right.
them being around it, being distinct from each other, not being
Right.
just even smeared. Yeah.
right.
You want to be careful about that because, like I said before, it gives you the idea that you have this discrete particle moving around.
Right,
It's not
no,
that
it's
at
not.
all. But yeah, you're right. It is useful for understanding the distinction between different ones. Okay, so I think we already talked about this, kind of the properties that arise. We have these different groups, periods, blocks, and these things all have things in common. And those things that they have in common come about from the way that their valence orbitals are filled with electrons. And so we're going to talk about this more, but I just wanted to make sure I introduced this idea of kind of the families of different atoms early on. Okay. I think we already talked about this. But so electrons, so why are they arranged this way in the periodic table? Electrons occupy these clouds, or orbitals. There are orbitals contain 2 electrons, and those 2 electrons are at the same energy level. The lowest energy orbitals are always filled first, and so we're going to kind of progress through the way that we can kind of construct atoms and understand what goes into them and hopefully piece together what's going on. And so there's convoluted or esoteric names like the Abel principle for this. There are 2 electrons per orbital, and no more than 2. This is called the Pauli exclusion principle. You look very confused by this?
Keep going.
For the first one, I thought after that there's more than 2.
Yeah.
Same.
No. There are.
Like 2 for.
Knowledge.
We'll get into this a little bit more. There's always 2 per orbital, but as it gets larger, you'll have more orbitals that are available. So there's the s orbital, which is only 2 for that first row. The second row has an s orbital and p orbitals. It has 3 p orbitals.
Oh, so
Oh.
for
So
just
each of the p
S
orbitals can
has
hold 2. Yeah.
And then,
And then there's 3 p orbitals, which each hold 2 electrons. So orbitals are always holding 2 electrons. We have to look at how many orbitals are available for different rows or different places in the periodic table. And we're going to keep
It's,
adding information to this, so hopefully it'll become clear. Okay, and then the last thing is, as electrons fill into these orbitals, so like we just talked about, there's 3 p orbitals. When they go into these p orbitals, they want to enter one at a time. They don't want to be paired up with each other.
I want a copy of that.
You can have the whole presentation. Trim away what you want.
Please, 'cause I can't keep up. Cool.
Okay, so here are the actual orbitals. So here's an s orbital, and then here are the p orbitals that you were describing. So if you think about the p block, there are 3 orbitals, so there's 6 spots for electrons to sit. But there are actually 3 distinct orbitals. And then there's also the d orbitals, which is where the transition metals jump in. And we're not going to talk so much about the d orbitals, but you can see as you move down the periodic table, as the atoms get larger, so there's more protons in the middle, there's more electrostatic force pulling in electrons, you have more orbitals that come about. The math behind this is, I think, a little bit more complex than you guys need at this point. But I think it's a good enough foundation for what you need to know to teach them and for what they'll need to know moving on to the next step. Just to understand that there's orbitals, and these orbitals are what gives rise to the way we organize the periodic table, and then to the properties that come about, the reason why the families behaved in certain ways.
So we're no longer to call them shells.
Shells are fine.
Oh.